Ready? Hello. What's the matter? Yeah, I collected those. And did you have any test parts that you took home? Okay. All right. I'll try my best to get the test back tomorrow. So give it my best.
Don't worry, take your time.
Okay, take your time. All right.
Take your time.
All right, Hunter and Brandon, those who took the test home brought back their tests, and labs were due today. So please take care of that when you see me next. We are looking at Mod 5 called Newton's Laws. It turns out that you can start taking notes on the newest handout I gave you. It turns out that Newton, he actually changed the thinking of his day in so many fields. He co-invented the calculus, so some of you are thankful for that, right? And then there's this idea that he came up with, and it seems really simple, but it really revolutionized the thinking of his day, and it's still with us. What they thought, imagine this, they thought that if an object was, they thought that an object always wanted to be at rest. So, sort of like teachers and students, right? Yeah, especially on a Monday morning, you look like you understand that. So, for example, this eraser, I'm going to slide it down the table. And it wants to be at rest, so eventually it stops. So if I throw it a little harder, still, it wants to be at rest. So they all thought that every object wanted to be at rest. But Newton, he came and said that was not true. And you've all heard Newton's laws in earlier science classes, I'm sure. So let me dictate it to you, and you write it. Newton's first law, so write down Newton's first law. An object at rest will stay at rest, but here's the revolutionary part. An object in motion will stay in motion. So that was what they hadn't gathered yet.
Can you repeat that again, please?
Yes, I'll read it a couple times. Newton's first law, an object at rest will stay at rest, and an object in motion will stay in motion. And then the word unless. So wait till you get up to unless. Does anyone know how the law is finished? An object at rest will stay at rest. An object in motion will stay in motion unless, and what we observed there was the unless, because it didn't stay in motion. There was an unless. When you get to the word unless, I will continue. So far, an object at rest will stay at rest. An object in motion will stay in motion unless, ready? Acted upon by an outside unbalanced force.
Was acted upon by
Unless acted upon by an outside unbalanced force. Unless acted upon by an outside unbalanced force. So, there must have been some outside unbalanced force working on our cut up eraser here. What was it? What is the outside force that's applied to that eraser? Otherwise, it'd still be going.
Friction.
Friction, that's right. So in this case, the outside, and it often is, you could make a note of that. So let's say, why does an object stop? Friction. That's the outside unbalanced force that comes out and stops objects in most cases. Let's make a note about that. So you have the first law written out. You have it. I don't need to write it. Also, under the first law, it has another name, the Law of Inertia. So I might call it that. So near where you define Newton's first law, you can write it has another name, the Law of Inertia. That just means what I just said. An object at rest will stay at rest. An object in motion will stay in motion unless acted upon by an outside unbalanced force. That's the Law of Inertia. sometimes called Newton's first law. So be ready to recognize either way that I refer to it. So why do objects stop? And the answer is an outside force, unbalanced. I'm assuming you know they're unbalanced. If one force was countering another, nothing would happen. An outside unbalanced force, often friction. Let's define friction, or at least describe it. Often friction is that force. Friction always opposes motion. Friction, let's say a force that always opposes motion. The object wants to go one way and friction will oppose it. So let's talk about riding in the car. We have a car. Of course, there's a physics class, we have a car. Alright, so here's a car, and let's see, this is a person, if it'll stand up. Golden person here. So if the car's going along like that, the car has a velocity, and the person has the same velocity as the car. So what happens if the car comes to a sudden stop against the purple book? Alright, so watch the person. Oops. Don't watch the person. Wait, watch the person when I get it going here. Alright. What happened to the person?
Didn't wear a seatbelt.
Yeah. Alright, so you can see the person start. I'll put him in the back seat even.
Where did he going?
Alright.
Go forward.
Every time the car stops, the person went forward. So if the car and the person have the same velocity going down the road, the car stops and the person still has that velocity. So they keep going. So, yes.
Did you know that on military planes, certain ones, I've ridden on them, it's like they have the seats backwards, so when it's flying, in case it were to crash, the force would go backwards, not
It's
forward.
better on the body.
Yeah, apparently
Yeah.
it would save you instead of
Right.
going forward. So the entire time you're flying, you're going backwards.
It seems like
8.5 hours.
it seems like it would be better on the neck because you would
Yeah,
hit
You'd go down,
you hit this.
boom,
yeah,
you go forward.
right. Interesting. Makes sense to me. All right. So when we're talking about the car and so forth, what if, have you ever been in a car that stopped? Did you
Yeah.
fly across and hit the windshield?
We should have.
What stops you?
Seatbelt.
The seatbelt? What if it was in the olden days, or even on buses? Go figure. Why do buses
The
not
front of
have
the thing stops you.
How come buses don't have seatbelts?
Apparently
It's
they don't
safer
need
without them.
They what?
It's safer without them.
Really?
Yeah, they
Yeah.
tested it with that many, like, that big and
I
that
was
many
always
people.
wondering that.
But the bus is pretty big, so if you think about it, if you get a car accident with the bus, I don't think the bus is gonna be the problem. I think the other cars.
But just imagine, like, you're riding along and it goes in a ditch. Wouldn't it be a little better to have a seatbelt?
It'll be a little uncomfortable for your head.
I
I
mean,
mean, if it flips over, then it would not help to not have a seatbelt.
Right, but I
guess,
mean,
but
the
then
Well, you better hold
the
on.
only thing
Yeah.
flipping a school bus is like an 18-wheeler or something like
but
that.
what about
Like,
just
you drive
coming
off
to
the
a
road
sudden
and you're like,
stop?
oh.
Wouldn't it be better to have a
Your face is
seatbelt?
flat.
I don't know, they
That's
tested it,
happened so
apparently
much,
it's
man.
more dangerous,
I
it was
gotta look
causing,
that one up.
it was
But
causing
anyway.
more accidents.
What about the times when your car comes to a stop and you have the velocity of the car
Oh,
stops, it's not sudden enough to send you into the windshield. So what is holding you from going forward? It happens all the time. Your seatbelt helps a little, you can feel the pressure. What about the olden days if there wasn't a seatbelt? Or you're on the bus? What is it? What force is preventing you from going forward when the car comes to a stop? Friction between what?
You and the seat.
Your butt in the seat. That's right. So,
Oh, yeah.
all right. So
Funky
friction is our friend. It is our enemy. So, your body should continue when the car comes to a stop. And friction, the seatbelt, the windshield, something is going to stop you. Another force will stop you. All right. wonder if there's anything else we need to say about that first law. I know you've heard it before. What about the other way? What happens to the person in the car who has the velocity of the car, but the car speeds up all of a sudden? Whoop.
Yeah, that goes back.
Move that.
Move that.
Move
Yeah, it goes
that.
back and you end up in an empress.
Alright, so now so this time, the car and the person have the same velocity, but then the car gets faster and the person still has the old velocity, so it will go
Is
backwards.
that like when you go around a
Yeah.
turn, you're
Yeah.
always like leaning on the people
Right,
next
I
to you?
remember when
I've
my
seen that before.
daughter, second daughter, you don't know her, was little. Her job would be to carry home pizza in her lap, and I'd tell her when we go the curve, it's gonna move every time the pizza would go down in that little spot between the door and the cushion.
Oh, that's
So-
horrible. Yep,
She-
probably had to like try.
She couldn't get it.
Clean that
Or
Well, at
she
least
couldn't
it puts
remember it
cheese
long
on
enough to get
Yeah,
home,
that's
so again.
That's
Inertia, it
What's the
is our
jelly
enemy,
pizza right there,
it
man?
is our friend. Alright. You'll be answering some questions in a minute about the law of inertia, so let's go ahead and look at the second law, because that's on our list for today too. Let's look at law number 2, and I'll write it in words or dictate it, whichever.
Okay.
I think I'll write this one. We'll say it like this. All the forces acting on an object so I'm going to add them all up. This is Newton's second law, Brian. You can write it down. All the forces acting on an object equal mass times the acceleration. I write it in words probably the first and last time because normally it'll just show up. When we want to say all of in math, we use this symbol. It means the sum of sigma notation, F equals ma. So the second law can be written more concisely. The sum of the forces equals ma.
Which pal?
Mm-hmm.
How
How
long
many
do-
minutes?
I don't know.
All right, we better stop then. We're gonna
Well,